Cauchy integral formula is very powerful. So we're gonna prove few results, all of which are some key results in complex analysis. And also we'll prove a fundamental theorem of algebra as well. I know it's a complex analysis class, but we could do it. So let's see how that's done. Let's jump right to it. Okay, so the first thing I want to show is Cauchy's estimate. So this is using Cauchy integral formula and using the ML estimate on top of that. So suppose you have an analytic function f in an open set containing some ball of radius r centered at z0. And in that disk, or in the boundary, sorry, suppose that the function f is bounded by some constant m. Then we could show, we could have an estimate for every derivative of this function based on the maximum value of this function on this boundary. Okay, let's see how this is proved. Okay, so we want to prove a bound on the modulus of the kth derivative at z0. So we're going to first use the Cauchy integral formula on this circle radius r. And what we're going to do is we're going to use the ML estimate, right? So we put the absolute value inside of the integral. We know that the numerator is always bounded by m. And the modulus of the denominator is always equal to r because we're on a circle of radius r. So we get this estimate inside of the integral. And the circumference of the path is going to be 2 pi r. So the 2 pi cancels out there. And 1 power of r gets canceled out by the 2 pi r part of it. What we're left is what we have. So that's the Cauchy's estimate. This is a great way to kind of control how this function behaves, like all the derivatives, just by looking at the value of the original function. Very useful estimate. We could use this to prove Liouville's theorem, which is a very useful theorem. Let's see, we have an analytic function on the entire complex plane. So it's an entire function. If f is bounded, then it has to be constant, which is a pretty strong statement. You just have to show that it's bounded and the whole thing has to be constant. Okay, how would you prove that? So suppose it's bounded by m. Okay, then we can use Cauchy's estimate to show that the derivative is less than or equal to m over r, right? Like so first derivative is just the first power. So we just put the r there. But this function is true. This estimate holds for any radius whatsoever because it's an entire function. So just knowing that this is true, it's a fixed value of m, we can make the r as large as we want. So the only way this could be less than or equal to m over r for all positive r is if the derivative was 0 to begin with. So f prime is 0. And there was nothing special about this z0 in the complex plane. You could have done this argument anywhere else. So the derivative is 0 everywhere. Therefore, f had to be a constant. Okay. You might think that function being bounded is a strong condition. So maybe it's not as useful, but if you think about that theorem, as long as you can find an entire function that maps to a bounded function, then you could show that the function is also constant as well. So let me give you an example of something like this. So let's say we have an entire function. This doesn't have to be bounded, but suppose it's the real part is less than or equal to 0. So the real part is negative, or at least non-positive for all z. Then f must be constant. So how could we use Liouville's theorem for this? What we're going to do is we're going to use an entire function e, so e to the f, and claim that this guy is constant. So let's see how we could do this. Well, the modulus of g itself depends on the real part of the exponent of e. So we have proved this in the past. And then the real part of the function g is the u. And this is the part that's non-positive. If it's non-positive, it's less than or equal to e to the 0. That's the largest it could be, which is 1. So we just show that the modulus of g is less than or equal to 1. So g is bounded. So g is a constant function by Liouville's theorem. But if constant is equal to e to the f of z, then take the natural log of both sides, and then f has to be constant as well, because f is a natural logarithm of a constant. Okay, so this is just one example, but if you can find a function, entire function that makes the function bounded, then you can show that the function is bounded. Okay, next let's prove the fundamental theorem of algebra. Okay, so what does fundamental theorem of algebra say? Suppose we have a polynomial of some degree n, and let's say n is a positive power. And all of the coefficients, ai, are complex numbers. And to say that this is actually nth degree polynomial, let's assume that the leading coefficient an is non-zero. So if you have a polynomial of degree n, then it has to have a 0. The polynomial has a 0. Okay, let's prove it. So we go by contradiction. So suppose there exists a polynomial p such that it has no zeros. So nth degree polynomial with no zeros. If it has no zeros, then 1 over p of z is an entire function, because we're no longer dividing by 0. So every z makes sense here. And let's focus on the modulus of the polynomial. Instead of writing the polynomial, we're gonna factor out the modulus of z to the n. So we have the leading coefficient an by itself, because we just factored out z to the n. And every other coefficient, when we factor out z to the n, we divide by some power of z. Okay. And we're going to use the triangle inequality, the reverse triangle inequality, to show that, well, if z is large enough, all of these guys are going to be closer and closer to 0. And if you have an, I guess, in modulus, and then we're subtracting these terms that are going towards 0, then eventually, this is well approximated by z to the n times a to the n. Okay, or it's a modulus of p is at least as big as this expression for large enough z. So I know we're subtracting a little bit, so we could say greater than or equal to absolute value of n divided by 2, for example. Okay, so this part is constant. So as z blows up to infinity, this thing will become huge. So this means that, so if p is blowing up to infinity for large z, then the modulus of f is approaching 0 because f is 1 over p of z, and denominator is blowing up, right, as z gets larger and larger. But then by Liouville's theorem, f must be constant because look, if you pick a large radius, so let's say this is a complex plane, we pick a large radius, the function f is bounded because it's a continuous function in a fixed circle. It's going to be bounded. Everything outside this large radius is going to be very close to 0. So it's less than some constant 1, for example. So it's bounded inside of the circle. It's bounded outside of the circle. The whole function f is bounded. So it's an entire function that's bounded. So it must be a constant, which means the polynomial is constant. And this is a contradiction because we said this was a polynomial with some positive power of z. Okay, so this proves fundamental theorem of algebra, but maybe this isn't the form of fundamental theorem of algebra that you know. So this, what I proved was that there's at least one 0. But if you find a 0, you could factor that outside of the polynomial, and then you have an n minus first degree polynomial. And then you can repeat the argument again. So this implies that any polynomial can be completely factored in C, where you could rewrite the polynomial this way. You have a leading coefficient an, and the rest of the polynomial could be written as z minus the 0 of this polynomial. And there's going to be n different zeros for nth degree polynomial. When I say n different zeros, they're not necessarily distinct. There could be double root or triple root, right? So this z j could be repeated. But yeah, this proves the fundamental theorem of algebra, which is pretty cool. I think, yeah, one more consequence and in this video. This is again a very useful theorem, and it kind of adds to intuition of how analytic function have to behave. So this is called the maximum principle. Okay, suppose we have a function f in analytic in some domain D, and pick a point somewhere inside of this point domain, and suppose the function is as large as it could be in the domain at that point. So the maximum happens somewhere in the domain. If you have this situation happen, then f has to be constant. So this means that, of course, function is changing values all over the place. For analytic function to be not constant, that means that the maximum modulus has to happen at the boundary, not inside of the domain. Okay, let's see how this is proved. Okay, suppose z0 is a point at which the function achieves its maximum inside the domain D. And then we'll use the Cauchy integral formula around that point. So the modulus there looks like this. And let's pick some radius r around that point z0. R small enough so that it stays within the domain D. Okay, so we'll parameterize the curve on some circle of radius r. We can plug that in for z there. And here's the derivative of that path. Okay. In the denominator, the z naught cancels out. And after they cancel out, r e to the ti cancels out with the r e to the ti here. I have this I left over, but when we look at the modulus, that doesn't change the modulus. So if I put the absolute value inside, that is the modulus we're looking at. But I could estimate this from above by absolute value of f of z naught, because that's the largest modulus the function could have in the domain, right? Not these values cannot be larger than that. Okay, but now I have the integral of this constant from 0 to 2 pi times 1 over 2 pi. So the 2 pi cancels out, and we get the modulus of f of z naught. Now, what did we just compute? We just started with this and ended with the same expression. It seems like we went back in circle, but we actually gained something. We made some estimates along the way, but for you to end up with exactly the same value at the end, that must have meant that every single inequality in this computation had to been equality. That's the only way you could end up with the original value. Okay. So in particular, when we were comparing this guy, looking at the modulus of the function in a circle surrounding z naught, these modulus was not any smaller than the modulus of f of z naught. That means you have to have the equal modulus throughout that circle. And there was nothing special about the radius r that we chose. We just chose a small enough r where this is true. So that means that I could have changed any r here. This function is constant on this disk of radius r and below. That means that function f had to have a constant modulus. And we have proved in the past that constant modulus implies the function is constant. Okay. All right. I'm going to end the video here. I'll see you guys later.